Hello everyone! We don't have an official pre-lecture video for today's content because we already covered it a lot in the lab. So during week 2 we did the molecular modeling lab and we talked about acyclic molecules. We talked about how you were going to get Newman projections based off of the regular structure for butane, and we also showed it for ethane, and then we also talked about the stability of those. So if that doesn't sound familiar, you might want to go back and review that lab lecture. And what I thought I would do is, since we've already done all that, I would use this time to instead talk about the activity that you would do. So basically going to apply all the things that we learned about butane to new molecules. All right, so now that hopefully everyone's up to speed about butane, that's really great, but how helpful is that? How many times are you going to be looking at specifically butane in your life? Probably not very many, right? So we're going to take it a step further now. What we want to do is take what we learned about butane and transfer it to a new system. And this is going to help us sort of understand the stability of things based on their structure, which is really important. So what we're going to do is figure out Newman projections and energy relationships for different acyclic molecules, meaning like open chains. So we've had this activity. This should be posted on Blackboard for you guys. So I just wanted to go through it with you guys to make sure everyone's on board. The ultimate goal is that we want to be able to show the lowest energy conformer and the highest energy conformer of any acyclic molecule. But in the process, we have to first practice drawing Newman projections of things besides butane. So that's where we're going to start. So as you can see for problem 1 here, it says we're going to draw a Newman projection of 2,4-dimethylpentane. And it's also going to tell you which bond to look down. That's really critical. So this says to look down the C2-C3 bond. So let's look at the process for that. All right, so step 1 here says we're going to draw the molecule in line bond form. So as you can see, I've already done that to the right. We've already done naming, so hopefully that looks familiar, but if not, you can go back and review that. All right, so then the next step is we're going to locate the correct bond to look down and then add any hydrogens to that key bond. So if you look over here, here's my little eye. Sorry, it's kind of creepy. But if you look down this, we want to look at the C2-C3 bond. So we're just going to number it like we do for the naming. So you can actually start from either side in this case, but I just started on the left. It's symmetrical. So this would be C1, and then C2 and C3 are labeled here. So now I like to circle those just to make it more clear. So I circle that one, and then add any hydrogens. So how many hydrogens will we have on C2? Right, we have 1 hydrogen there because we already have 3 bonds. And then for carbon 3, how many hydrogens do we have? Right, we just have 2. So now that step's done. So now let's look at step 3. So for this step, we're actually going to start drawing the Newman projection. So it says to first draw the front carbon, then draw the back carbon, including the hydrogens, and then we're going to end up adding them together. So eventually you'll probably just do that, they'll actually be combined instead of separate, but I really wanted to separate them here so you can see which one's C2 versus which one's C3 before I add them together. So that's what we're going to do. So for C2, that's the front carbon here. It looks like a little just Y. We're going to add the groups on there, and it's really important for Newman projections. The convention is to always use condensed form and not line bond form. I don't know why, that's just how it is. So we're going to use like CH3 for a methyl, CH2CH3 for an ethyl, whatever it is, and make sure you have the carbon with the right amount of hydrogens attached where it's actually attached, okay? So for carbon 2, if you look at carbon 2 up at the top, we've got 2 methyl groups and 1 hydrogen. So all we have to do is add those 3 groups, and then we're not adding C3 because that's going to be the back carbon, so we're just skipping that one for now. So this is what it would look like. I added my CH3, and my hydrogen. It doesn't really matter right now the order that you add these in, or if you put the CH3 instead of on the bottom, if you put it on the right, that would be fine. It just matters that you have the correct groups, which we know from matching it from step 2, technically, the one I drew at the top. Okay, so now let's look at the back carbon. For the back carbon, we've got those 2 hydrogens from C3, but we also have this other group that's got 3 carbons on it. That's an isopropyl group. That's not part of the name, but that technically would be an isopropyl group. So if you look, we're just going to use condensed form. The part that's attached to the C3 is going to be the CH here. So let's draw that first. And then we can draw the other CH3s attached to that CH. So I'm just going to do it as CH3 too, since they're both the same, and then that gets that job done. And then the next thing I would do is add the hydrogens, right? Because I have 2 hydrogens. So perfect. So then before we move on, let's double check that we've got everything the same. So C2, that's this one here. We're going to have a CH3 group, and a hydrogen. For the back one, the big circle, we're going to have isopropyl group H and H. So that's perfect. Notice we have every carbon we're accounting for. You just have to remember that for this one, you have CH3 dot. The dot in the middle of this would be like the carbon. And then the back carbon is that big circle. So you don't want to add any more carbons than you're supposed to have. It's only supposed to have a chain of 5. So we go 1, 2, 3, 4, 5. And then there's obviously 2 extra methyls. So then that's perfect. That's the most common mistake that students make, is adding extra carbons because they don't account for the pink one and the green one as the dot and the big circles. So just make sure you do that and you'll be 90% of the way there. All right, so let's keep going. We're just moving down the activity now. So step 4 here says to combine the 2 pieces of the Newman projection by putting the front carbon on top of the back C. So we're basically just going to combine these two. I've brought them over from the other page, and that's how we're going to do it. So I like to draw the back one first like this, and then I'm going to put the Y in the front, and then I draw my back carbon, the things that stick out from it. Notice when I drew this that the ones in the back are exactly in the middle of the ones in the front because it's going to be staggered. So make sure you do that. Make sure that the ones from the back are sticking out in the middle and they're not like super close to the side. So that way we can tell it apart from eclipsed. So this one, as you can see, when I put them together, is going to make a staggered, but it's going to depend on the energy, which one you want to make. But let's just put them together the way they are right now. And then, of course, now we're going to add the groups. So for the front carbon, I'm going to add a hydrogen, a methyl, and a methyl. And then for the back carbon, I'm going to add my isopropyl and then my 2 hydrogens. So now we have the final product, which is a Newman projection of the molecule that we were talking about, which was 2,3-dimethyl pentane. And remember, you can do pentane and other things. It doesn't have to be a butane. Sometimes I'll call them butane conformers just to make it clear like we're doing them like butane, because that makes it easier for you guys to remember. But it doesn't have to be butane to be, quote, butane conformer. So always write it in quotes. Okay? So then once we do this, generally we're not going to just draw it randomly. We're going to draw the lower and higher energy conformer. So let's talk about how we're going to do that. So as a reminder, we talked about highs and lows of energy forms for butane itself. The highest energy will have what kind of torsional and steric strain. So those are the 2 sources it could have, either torsional or steric. Should it have higher or lower of those? Right, it should have the most torsional and steric strain because higher strain is higher energy. And remember, higher energy means it's less stable. So that's actually the bad form, the form that the molecule doesn't prefer. Okay, so then the next one says the lowest energy. So if this one has the most, this one's going to have the least torsional and steric strain. And so that's what we're looking for. So now the question is going to be, how are we going to draw these to make that happen? So for the highest energy form, remember that's going to have torsional strain. It's going to have eclipsed interactions. So what we're going to do is this. First, we're going to line up the biggest groups. This is going to ensure that we have the most torsional strain and also that we might have some steric strain, just like we saw with the fully eclipsed form of butane. So we have torsional strain because they're lined up, just because the bonds are lined up. So the big groups are together, they might bump into each other, and that's what we are looking for if we're looking for high energy. All right? So then the other thing we'll do is if we have different kinds of groups on the front and the back, is that we'll line up the smallest groups. This will ensure that the second biggest groups are together, which is really what we're trying to do. So if you line up the biggest and the smallest, you'll have the very biggest group together, the second biggest groups together, and then the least big groups together. And then that's going to cause the most steric strain. So that's what we're looking for. So now to get the lowest energy, we're going to use a really similar process, but just do one part different. So what we're going to do is now we're going to take the 2 biggest groups and make them across from each other. And remember, that's exactly what it looked like for the anti-conformation for butane. You take the biggest groups and they were across from each other 180 degrees and everything's staggered if we do that. And then we might have more than one group on there, so then we're going to put the smallest groups across from each other. And just like before, if we do the biggest and the smallest, that will ensure that the 2 medium groups are the furthest away from each other. So that's going to cause us to have the least steric strain. We may have some extra gauche interactions based on how many carbon groups you have attached to your C2 and C3, but at least you won't have the biggest groups together right by each other having the gauche interaction. You'll have smaller groups next to each other. So that's the goal. And just a reminder for these, we won't have any torsional strain because everything's going to be staggered. So torsional strain comes from eclipsed and it's not eclipsed. So because they're staggered, we won't have any of that problem. All right, so now that we sort of got that in hand, let's actually try it out. So the last thing we're going to do is rotate the Newman projection or just draw it from the way that's going to give it the highest or lowest energy based off what we just saw. So I'm going to put the ones we had from before, here it is. And then we're just going to redraw it in the form that will be the highest energy first, because that's the first part. So the first thing we're going to do is just draw the basic eclipse structure because we know it's highest energy and we want that torsional strain. So we'll draw it like this. So that's what an eclipse would look like. Notice for the back carbon, I put them really close to the front carbon ones, but I have to leave a little bit of a gap just so you can actually see what's going on. And I also make either the front or the backs a little bit longer so you can kind of see them whenever you start writing the things on there. So let's add our groups in the back. We can generally put them anywhere, but I'm going to put the isopropyl on the top in this case. All right, so that's my back carbon. Now I want to put the biggest group with the biggest group. So the isopropyl is my biggest group in the back. So what's my biggest group in the front? Right, it's going to be a CH3. So it doesn't matter which one you pick, we're just going to write a CH3 there. All right, so then we want to put our two smallest groups together. So what are our two smallest groups? What's on the front that's small? It's a hydrogen, right? So let's put this hydrogen with one of the other hydrogens. It technically doesn't matter, but if I'm rotating, I guess I'll put this one here. And then the last thing we're going to do is put our medium groups, right? The group left over. So just add your medium group. All right, so that's our highest energy conformer done. We've ensured there's torsional strain because the bonds are all lined up, it's eclipsed. And then we've put our big groups together, our small groups together, and our medium groups together. In this case, we had two that were the same, but that's fine. So let's do the same thing with the lowest energy conformer. So let's draw the basic lowest energy conformer, which would be staggered. So we'll draw that. We can kind of draw the same shape as this other one. And then the next thing we're going to do is add the groups. So I'm going to keep the same back carbon. I think it's just easier if you keep one of them the same, and I always prefer to put the back one the same because it's easier for me to see the rotating front. So there's the back one. I'm adding all my groups. And then we're going to add the front groups. So what is our biggest group in the front is the same as previously, right? So we said that was a CH3. So what are we going to do with that CH3? Right, we're going to put it across from the isopropyl, so it'll be down here. And then the next thing we're going to do is just add our smallest group across from the smallest group. So we need a hydrogen across from a hydrogen, and that's actually fine. We can draw it like that. And then our last thing is the medium one. We just put it in the spot left over, so we're going to put it right there. And then that's done. Now, if you're looking at this, you may say, hey, this green one kind of looks a lot like that purple one. If you look, all the groups are the same across from each other, but the whole thing overall is a mirror image. So based on the way I happen to start it, in this case, either one of these would be correct. For the lowest energy conformer, they're basically the same. It really depends on how you draw it for your first one, where you start it. So I don't really know what your first one looks like, only you do. So it may not have been the same, and that would be okay too. But now these should be the same. The lowest energy conformer and mine and yours should be the same, or it could be a mirror image, but it should be staggered and the same group should be across from each other. And the same thing with the highest energy, it should be the same as mine, or it could be the mirror image, like if this CH3 in the front was on the left side instead of the right, that'd be fine, but the same groups are lined up. So that's the key. All right, so now that we've done one example, I'm gonna leave it to you to do the other two examples on that activity. So those are the ones that you'll try out. Basically, to get that, you just go to Blackboard in the activities folder like you normally do, and that's where you're going to find that one. Also, if you look, the answer key will be in the answer key folder. That'll pop up probably the next day after we were supposed to do the activity. Hopefully you found this helpful. Make sure to try the activity like I said and check your answers. Let me know if you have any questions. Have a great day. Bye.